Derivation of the de Broglie and Planck-Einstein relations. In the first chapter of this series of videos called the Cyclical Universe, two velocities v sub p and v sub g appeared, which were identified as a phase and a group velocity respectively. That made us realize that the wave nature is also present in our analysis. Now it will be shown that the de Broglie and Planck-Einstein relations, which historically were the first expressions that revealed the wave nature of matter and the corpuscular one of light, also appear here naturally. Let us consider the following situation: a train car with a bar with hanging oscillators. From inside the train, which is the S' reference frame, these oscillators are seen to move in phase with their own frequency f sub 0. However, these same oscillators, when observed from the platform, are seen to oscillate in a slow motion due to the time dilation, and also they are seen to move with a certain out of phase due to the relativity of simultaneity. This out of phase situation, observed from S, generates a phase wave with a well-defined wavelength lambda sub p. Let us analyze this same situation, but in the rotated axis representation first introduced in Chapter 2. In that video, the lens contraction was derived using a similar situation. In that case, though, the bar had no oscillator. We now draw the bar at the origin of the S' reference frame and temporally evolving on the T' axis. Let the oscillators be drawn now, a few less for simplicity though. We also draw the length L' of the bar, the length L of the bar seen from S, the theta angle that determines the relative velocity between the train and the platform, the proper period of oscillation T sub 0, and also how this same period is seen from S. Let it be called period of the oscillators T sub OSC. Then, for this particular relative velocity between the train and the platform, that is, for this particular value of the theta angle, there are two oscillators located on the x-axis of the S reference frame. Note that in this figure, all the depicted oscillators are in phase in S'. Therefore, the two oscillators on the x-axis satisfy two different things. They are in phase in S', and they are also simultaneous events in S. This is to say that these two oscillators must be in phase in S too. Then it follows that the distance L between them must be equal to the wavelength of the phase wave. Maybe this is better seen in this other representation. See that on the x' axis, all the oscillators move in phase. In contrast, on the x-axis, only the oscillators A and C are in phase, while B is in another state of vibration. Therefore, the distance AC on the x-axis is the wavelength of the phase wave when observed from S. From the diagram, one sees that L and T sub 0 are related through a projection according to the star sign of theta. Replacing L by lambda sub p and then writing the expression of the relativistic momentum found in Chapter 3, one can replace the star sign function by an expression containing p. Then, by isolating the momentum p, the wavelength moves to the denominator, and the numerator becomes an expression that, written as a function of the sub-zero frequency, reminds us of the Planck's constant when isolated from this other expression. This other expression will be justified in later chapters. In this way, one obtains the de Broglie relation. Let us now derive the Planck-Einstein relation. The frequency of the phase wave is the phase velocity of the phase wavelength we have just found. In Chapter 1 of this series of videos, the expression for the v sub p was given, and here we write it in terms of theta because in this diagram above, theta equals alpha. Substituting these expressions, one finds that the frequency of the phase wave, when observed from S, is the proper frequency f sub 0 multiplied by the star cosine. Then, multiplying by Planck's constant on both sides and using once again the expression that relates the frequency with the rest mass, the expression of the relativistic energy appears on the right. Thus, E equals h times the phase frequency. This is the Planck-Einstein relation, which is valid not only at rest but in other situations with relative motion. That is to say, the fact of having used hf sub 0 equals m sub 0 c squared means that the energy of an object at rest is given by the natural frequency of its oscillators, and as soon as this object begins to move relative to the observed energy is not h times the modified frequency of the oscillators due to the time dilation, but is h times the frequency of f sub p of the phase wave that appears along the line of oscillators due to the relativity of simultaneity that comes with the relative motion. Let's see now how the phase frequency and the frequency of each oscillator relate to each other. From the drawing, we see that the proper time t sub 0 is related to the period t seen from S through a projection by means of the star cosine. By expressing this same relation in terms of frequencies and by comparing it with the expression of the f sub p that was just found, one realizes that multiplying both expressions, a constant is obtained. That is, these frequencies are inversely proportional. Let's do now the same analysis in terms of a space. The displacement of an oscillator when seen from S during a period of oscillation is v sub g times t. We now express the observed period according to the time dilation formula, and the velocity v sub g according to its expression that was found in the first video. Multiplying this result by the wavelength of the phase wave we have just found above, and expressing the result in terms of a product of frequencies in the denominator, then it is seen that if the frequencies are moved to the left of the equation, one recovers what we already know, the fact that the product of velocities is c squared. This somehow confirms to us that what we had called v sub g or group velocity is the actual velocity of the object, in this case the velocity of the bar. Therefore, the frequency of the oscillators can be called group frequency. We now write all the expressions we have derived, specifying in each case whether the appearing frequency is a phase or a group frequency, and so for the wavelength. So, what we are saying is that we initially assume that a particle can be understood as a bar with hanging oscillators. Such a model seems to work to describe what a particle is, which is quite revealing by itself. We now summarize the results. When the particle is at rest with respect to us, we see that all the oscillators move in phase with the frequency f sub 0. But as soon as there is relative motion, we see that these oscillators move up and down in a slow motion due to the time dilation effect, and also an out of phase appears between them. This out of phase generates a phase wave along the line of oscillators with a well-defined wavelength, velocity and frequency. Then the wavelength of this phase wave is what ends up determining the momentum of the particle, and the phase frequency is what determines the particle energy. Therefore, note that both the momentum and the energy are determined by two quantities that refer to the collective motion of the oscillators. They are not directly related to the properties of each oscillator itself, such as the frequency of each oscillator, but are linked to the frequency of the collective motion. This is the many-body motion. This situation reminds us of the waves that appear over the fields in the spring. The spikes would be the oscillators, and the speed of the wave over the field would be the phase velocity. The wavelengths of these waves would determine the momentum of the particle, and the division between the velocity and the wavelengths would be the phase frequency that would account for the energy of the particle. That's it for today. Thanks for listening and see you soon.